of the code during the last years, and understand how we can improve our applications to run fast and safe in 2020. So, and understanding that, we will understand some Ruby limitations and how to deal with those limitations, and how to improve your applications using some Ruby resources. Okay, so before we start, I want to reveal some important things that we will hear a lot during the meeting. And so I will try to be brief and just do a recap, because probably most of us know what are that things. So okay, the first thing is, what are processes and threads? Okay, so a process has a bunch of threads. Each thread has a lot of instructions. Instructions are commands interpreted by the processor. Each thread is processed for a short time, and then other one is processed for a short period again. The chain between threads is called context switch. A context switch can occur in the threads from different processes. And the OS scheduler, the operational system scheduler, defines which thread will be processed. Okay, just some points, and I have some mates to represent. So here we have our process and some threads, and the blue ball represents our operational system scheduler. So the scheduler, so read the thread for a period, and then change, and then back again. And okay, I think that's it. Basically, that's it. The next point is, what are concurrence and parallelism? Okay. Concurrence occurs when we have context switches and or process flow, as we can see in the picture. Parallelism occurs when two or more processes are running at the same time, like the second mage. Concurrence and parallelism can coexist. So you can have those two things in the same universe. One is not an opposite to the other one. And again, we have some pictures to represent what was said. Concurrence, we can see some processes doing a context switch to be executed. And the second picture, we can see a parallelism, two processes running at the same time. And here another one example. And okay, so this is the our review. I think if we could understand what are those things, we are able to go ahead. And okay, the first thing is, um, the free lunch is over, and why I'm telling you about it. It's a famous article that explained how worked the evolution of processors. So this article explained why we don't have a 10 gigahertz processor actually, and why instead of that we have um, processors with a little core, but more cores. So actually we have acta cores. I don't know, many cores, but that course has small speed, clock speed. And we have this is the most important picture that I found in that article. And all the presentation was inspiring in this article. And basically, this is the most important thing for us now. So we can see the green line when the transistors are being increased on processors. But in 2005, please remember this year, it will be important during the presentation. 2005, the gigahertz of our cores stopped to be increased. So basically, we keep in 2 or 3 gigahertz, but the processor industry start to create more cores in the same processor. Okay, so and what was changed? For many years, programmers had slow applications, and the solution for that was wait for more gigahertz. Okay, probably no one here lives in that time because it happens, I don't know, 25 or 30 years ago. And I probably found this information in a book. So, and basically it happened in the past. So if you have a slow technology or a slow application, probably in 2 or 5 years, your application will be able to run correctly because we had a lot the gigahertz of our processors being improved every year. I think that stopped in 2005. Okay, in 2005 it was changed so that the processor clock frequency was not increased every year, as I told you. Okay, actually, we have multi-core processors, and to have a good performance in our applications, we should know how to program for multi-core processors. Okay, this is the point that this is the reason why this presentation was created. Okay, so important point. Should I be worried regarding multi or single core processors? Yes. So I understand what parallels is. I just have to run all my code at the same time and it's solved. No. Yes, I don't know. Okay. So or better, I have a better image. Okay. But this is not the point. Okay. No, you can't run all the code at the same time because you have Gil. Gil is there to destroy your plans. But what is Gil? Gil is a global interpreter lock. Basically, a lot of language based on C based has the same limitation, the global interpreter lock. And when I say Ruby MRI, I'm talking about the C Rube, the Rube that run in a C virtual machine. We have another versions like JRube that runs in a Java a virtual machine or Rubinius and other ones. But in this presentation, we will talk about Rube MRI. And Rube MRI can't run 2 instructions. We talked about instructions in the beginning of the presentation. Can run 2 instructions at the same time. Okay, except IO instructions. And when I say IO instructions, I'm talking about network, the be write and write and read, in write and read in files as well. And because of Gil, Ruby MRI can't be parallel. So yes, Ruby MRI, the version of Ruby that we used in our in the normal day, it's not parallel, and it can't be parallel. Okay, but it's not too bad. Ruby is a multi-paradigm programming language, and parallelism could cause a lot of trouble. Yes, because definitely Ruby don't have the structure needed to run in parallel. So you can do it using a different version, but it could create a lot of problems. Okay, idempotence, referential transparency, and memorization and lazy evaluation. It are some concepts that we can find in Ruby. But and yes, before of that, we have to understand what is a pure function, because to be a totally functional programming language, you have to attend to all those points. You have to have a dependence, referential transparency, memorization, and lazy evaluation. And um another one, immutability, but Ruby does not have immutability. After that, sorry, um my cell phone, sorry. Mm, okay, sorry. um and okay, all those points, and Ruby don't have immutability. And I tell you, immutability is the most important point here to run a code in parallel, and you will understand why. So then we can talk more. We can talk more about those concepts, memorization, lazy evaluation, and other concepts that we can find in Ruby, and we can use to improve our code and the performance. Okay, going ahead. Here we have an example how Ruby on Rails works. So when the thread, we have two threads, and when thread A are running, creating an array or doing anything, the second thread is blocked, because you can't run two codes at the same time. And and when the thread B are running a code, the thread A is blocked, and we can see the why how it's working. Okay, and here, sorry, I can't find a picture with a better resolution, but I think we can understand. So as I told you, Ruby on Rails run in a C virtual machine. Okay. So and when I told you that Ruby can't be parallel, we have some exceptions in case of IRO instruction, or when we are running a C code, because as we know, we can run a C code, C functions, or C lib, and think we can do some things and call it as a native Ruby function. So I have a presentation about it, and we can do it in another opportunity. So basically, if you are running a C code, you can run in parallel. Okay, so yes, we understand what is parallelism, concurrence, and parallelism is the future, and because of that, we saw we understand the reason why we have more cores, and we don't have like a 10 gigahertz clock processor, so we have more cores to run code in parallel. So I'm telling you, the future is run code in parallel, and because of that, you can see actually more functional programming languages being popular than, I don't know, the 20 or 15 years ago. Okay, let's recap. Okay, Gil make Ruby MRI not parallel, except in IO transactions. Ruby can offer support to parallelism if it runs over JRuby or Rubinius. They are different versions of Ruby. And okay, it's not totally safe, as I told you. And you can find a real and good parallelism in Elixir, Erlang, Haskell, and Golang. Um, okay, we can use RubyThread resource to make our code faster. So okay, I think now we can start the, the important part of this presentation. Okay, I created a project and some simple scripts to understand how it's work. Okay, the first thing here is, sorry, um, you have those two codes. The first one here at your right, we can find code running. It's called a class. This class is uh, ship here. Okay, this class. So basically, we have a basic class, and um, we start the first state. Shorn is false, and when we call this method share this method ask, okay, the ship is shorn. If not, if true, if it's shorn, we just return. If not, we put a text on the console and check this ship as shorn. Okay, so let's run it. Um, Ruby examples and here. Okay. Okay, it's run, and you can run this code for many times and you will receive the same response. um okay, I will show you. We can run 10 times the same code running 10 times, and we will have the same uh, same output. Okay, 10 times we have just only one sharing message. Okay, for each running we have one message. Okay, uh it's okay, it's working fine. But what happens when we insert a thread in this process? um we insert thread. Okay, the second code, share 2. Let's try to run. It's run. Okay, so but now we running one time. We received only one message sharing. When we run again, we received two message. And what happens? And if we run again, probably we will have a random response. Okay, two again, and if we run again, one. But why it happens? Basically, when it happens, um, we find a race condition. Basically, it happens because we have a race condition, and it happens. And I will try to explain you why it happens. So, okay, let's go to see a different example. I will explain what is a race condition um, in a moment. Okay, different example. We have our database, Mongo TextDB, uh, and And okay, we just read the database, increments one in the number that is in the file, and then write again. Okay, count example. Okay. Oh no, no sleep. I have to remove this sleep. Okay. Hey, it runs 10. And okay, we write, and in the end of the file we have like a test. We run 10 times. So if we run 10 times incrementing one in the number, we must have a result of 10, because if you run 10 times and some one, that result must be 10. Okay, we can run this code for many times, and we will receive the number 10 as result. Okay, but again, when we try to add thread, the problem happens. Okay, let's comment it. Okay, okay, so we are running the same code but in a thread. What has happened? Okay, raise, and we run. Okay, we run 10 times, but the result is 2. Okay, and what happens? It happens because when we try to run, it's an IO instruction. So and as I told you, Ruby can run two things at the same time when we talk about IO transactions. And here we try to run the first time. Okay, we schedule 10 threads to run the same code, and then we call a join method. Join is the command to run a thread. And when we try to run 10, 10 threads at the same time, 10 threads go to the file, get a number, increments one, and save in the file. And probably 10, 10 according to the context switch, you probably have a random number, because you don't know when the context will be changed. And you can have three threads getting a number, incrementing one and saving. And it about probability. You can know what will be the response of that, because you are running at the same time. Okay, but we can solve this problem. We can create a mutex, and it will be solved. So basically, a mutex. I tried to. I was trying to explain that in technical, using technical words, but I think to understand it's better we have to use an example, a real life example. So imagine in a situation, you are in a discussion, a big discussion, and a lot of people are trying to speak at the same time. Each people in that discussion are a thread. So basically, we have a lot of thread trying to speak or do anything at the same time. And you said, okay, from now on, anyone that wanna speak have to rent a ball, and you have a ball probably. So okay, so to speak, you have to rent that ball. And okay, mutex here is the ball, because each thread, every thread, any thread only can speak or run anything if the thread hand the ball. And any code that is inside the ball will be running and waiting for the next one thread. So basically, the mutex here prevents to run that block at the same time. Okay, what happens when we try to run it again? Okay, the result it's okay, 10, 10, but the code looks like the first example. Nothing is changed. So okay, because we are working inside this block. But for example, when we try first thing, let's back to the first example. Okay, we have I will put I sleep just wait the time that you set here. So I'm telling to the application. Okay, wait for 1 second and continue your flow. So we will run this block 10 times, waiting for 1 second in each time. Basically, we will have to wait 10 seconds. Okay, let's wait. Let's wait. Mm, mm, Okay. Oh no. Okay. Here, the response. We wait. We run. The result was okay. Balance is 10. But the final time was 10 seconds. Why we waiting 1 second in each time? But what happens if we run the same sleep code in a thread? Okay, let's go. Yes, we run the same code 10 times, but in only 1 second. So all threads wait for 1 second at the same time. So this is the big difference between the first code and the second one. You wait, and when I'm telling you wait, I'm talking about any kind of wait. If you do a request, if you make a request to an endpoint, you have to wait the response, and wait don't consume your processment power. So you can, if you have to do I don't know, 20 requests for different endpoints, you can waiting for 20 response at the same time. So basically, this example explain about it. The mutex help us to solve the race condition problem, and the threads help us to improve our performance. So yes, basically that's it. Let's back to the presentation. Okay, just reviewing. Okay, again. So to explain, what the heck are race conditions? Race conditions exist when some pieces of data are shared between multiple threads. So, okay, our example, why the race condition happened in the chip example. Okay, we were running more than one thread. So, okay, in this example, we have two. So, okay, two threads. We try to run the first one, and okay, and the second one, but we don't know why in one moment Ruby basically could switch the context, and we don't understand because we don't have a documentation about it. You can look in the Ruby documentation, and you definitely couldn't won't find any information about how the context switch happens. And in for any reason, Ruby tried puts the message and switch the context, and then it runs a different thread, and the other thread do the same thing, puts a message, and then um, check the ship as shorn, and then back to the first one thread again. So basically, it happens here in our code, and it's the race condition. Okay, in the example, the read, when we were reading the file, this is the example. we try in one moment we try to read the file and we have a context switch and then increments in the different context, and basically we never could have a correct word, a correct word in our file and in our result because the context switch. So mutex in that situation helped us to deal with the switch context problem. Okay, and here we have some points. How to deal with race condition. So lock the file or database solves the race condition problems, but we lose performance. Not totally, because only the code that are locked will have to run in a sequence. But all the rest, as I showed you, um, runs in parallel. Okay. The next thing, we can use some functional programming concepts to prevent it and improve our code. Okay. So why do have I to use concurrence if it creates so many problems? Okay, we can find we could find the race condition problems and some others, but our performance in the final result was increased. And okay, the another important thing, try not to use thread new because it doesn't help you to deal with race condition. So basically, as we saw, we had to deal with the race condition manually. So actually we have a lot of good gens to help us with that. So probably a bunch of programs that are working to solve that kind of problems for many years, and in this situation it's safer use a gen than do all the work manually, and I will show you. Okay, code time again. Back into our code again, we have a Rails project. Basically I have a system to calculate a balance, account balance, and we have a bank account. um, we have a transfer and a user, and we have a controller to, yes, here I created a fake API, and this fake API, it's just an endpoint that we will send some requests, and this API will wait for 1 second and then returns an array of transactions. Basically that's it, and in this tab our API are running. Okay. So the important code here, we have a code to calculate or balance, and we just pass as parameter our bank account and then render the result. Okay. um, and or to calculate or balance, we have to sum all the incoming transfers, so everything that we receive, and we have to sum the outgoing transfers, so anything that we send to other people, and we have to sum external service. Yes, basically it's an value that we will get from or MPI API. Then we generate the balance, and then we serialize our bank account. Okay, so let's see those steps. Mm, Step here. So the first one is um, some incoming transfers. Okay, we don't have nothing complex. We don't have anything complex. We just we get from the database all the outgoing transfers, and then we sum the value. Then we go to the outgoing transfer. Okay, the same thing, only database request, and we sum all the values. Okay, so the important step here we go to we get all the values from our API. Then we call this API 8 times. So 1, 2, 3, and we will receive an value, and we will sum. And the final step is generate the balance. Basically, we will sum all the values. So all about we received less all that all of we sent, and then a plus external values. So I have a test for that, and here, okay. Basically, we create three we received three transfers. So we have $30. Then we send 20. So basically, here in this context, we have a balance of 10. But our external service always return $80. $80. And basically 10 plus 80 is 19. So if we 90. So if we run our test, spec request, and yes, it will. We have to wait because our NPI has a delay. We put 8 seconds of delay there. So basically, our example runs in 8 seconds. So basically, we here, and all the magic is here. All the magic is here because we each request we have to wait 1 second. So 8 requests, 8 seconds. Okay, it's real. It could happen in any, not wait for 1 second, because 1 second it's eternity for an API. But you a lot of times you have to wait when you make a request. And here we will see how to solve this problem. Okay. Um, yes, we saw this example runs in 8 seconds. Okay, so let's do the magic. Um, do it. It's just to change the branch. um, okay, git. This is the branch. Okay, here the magic is done. So let's open our example here, and let's open. Okay, basically here we have something different. We have this block totally different. And what is that? It's a famous gem to deal with concurrence, and it's called concurrent Ruby. Basically, it's a clone of a famous Java lib called Java Utils. I don't know, concurrence, anything like that. And basically, it helps us to deal with logs and files and database, and how to be care when be careful when we have to do it, run code in a concurrence. So basically, I'm using a promise. I create a promise, and in this promise, I send a request to our endpoint, and then it's anything that we have to run after the promise is finished. Basically, we send this, and then after this request is ended, we parse the response. Okay, here we are calling this method 8 times yet. So we call 8 times the method that then we execute. It's a method to run a promise in this lib, in this gem. Then the value, when we call the value method, we get the response of the promise. Then we just parse and sum the value. So let's run that same code again, waiting 1 second in each request. Okay, so we had 8 seconds in the first example here, but now the same code is running in 3 seconds. The same code, eight requests, and some all the values. The same code in 3 seconds. So looking for that, and okay, we can just to understand. We could we could um, put a lot of extras requests. So here, basically, we 20 times we are calling the same API 20 times, and let's go towards the response. Okay, our test is broken because we run more requests. So basically, we receive more money for external service. But the important thing here, most important thing here is we run 20 requests in 4 seconds, and in the first example, we run just only 8 requests in 8 seconds. So we can see here that help us to improve the performance of our code. And about the gen, the last thing I really recommend to use it, because this gen has a lot of resource related to database. So you can run anything, for example, of a code of active record, for example. And this gen has some research to deal with active records code. And so it's really helpful, and it will help you more than just use a thread.new. Okay, let's back to our presentation. Um, okay, let's review. RubMRI can run an app pretty fast, even without parallelism. So as we saw, we could run a code that run in 8 seconds. We could do it runs in 3 seconds. Basically, it was a really good performance improvement. So functional programming languages are faster, but sometimes you don't need of all of that power. Yes, you have to understand what each language could do for your company or your projects, and decide based on a reason with a good reason. Okay, so you can use Ruby functional research to improve your code. So basically, that promise that we used is a concept called monad, and monad is a functional programming concept. So and we have some others like that concepts that I show you in the beginning of the presentation, but I think it's a subject for a different presentation. The most important thing here is show you how to improve the performance using a non-parallel language. Okay, because of mutability, per functional programming language spend more memory, but they can use all the power of processors. Memory limit was a problem 20 or 25 years ago. Yes, the only reason why the functional programming languages are being used actually because I don't know 20 or 25 years ago we don't have like unlimited a memory source, you know. Basically, actually we can use a functional programming and don't have problems with memory limit. So please understand that extending Ruby for a functional programming language is a trade-off. You will solve a performance problem, but it will create some others. Yeah, because actually, in a lot of companies, not in Runa, we can hear something like, "Oh, let's replace Ruby to I don't know Elixir. Uh, uh, it will become our project faster." So yes, but it's truth. Yes, but we will have a trade-off. We will create different problems. So okay, closing comments. We saw more regarding the problem presented in 2005, dealing with multi-core processors. Yes, probably in 2005, we were bored trying to understand how Power Rangers could create fire explosions of grass. But actually, we have some other priorities. In 2005, 2020, and in the coming years, we should pay more attention to that, to how to deal with multi-core processors. And fire explosion on grass, concurrence is not important. So here are my references. So we have the link to the article, link to the RubyGen, and link to the GitHub repository. So that's it, and explosion.